Okay. Welcome to the lecture series, which is a part of the Simons semester about knots, homology in physics. And our speaker today and tomorrow, there will be a continuation, is Ramadevi from the Indian Institute of Technology in Bombay. And she will tell us about Chern-Simons field theory invariants, knot, links, and three-manifolds.
Okay, so towards the end of this set of lectures, I would at least give you a flavor of how to compute these invariants, especially the workshop which we had last week was on knots homology and so on. So I'm sure I will spend some time defining what is knot, what is link, and why this problem is a very important problem. Okay. So in mathematics, you can have a simple knot, if we call it as an unknot. Then you can also have a simple link. Let me use two different colors so that you can see the difference. You can have a link. Okay. So this is what we call it as a Hoff link. Okay, in the knots you can further draw. No, I'm not really very good at it, but I will try. Okay, so it is, you can see there's 1, 2 and 3 crossings. This is what we call it as a trefoil. And so on. Okay. So as this is only one color, which means it's only single curve, which is all these diagrams which I'm drawing here are projections onto the plane, which means they are not trivial in 3 dimensions. And when I project it onto the plane, some of the crossings will be overcrossing, some of them will be undercrossings. So 3D, these figures are non-trivial only in 3 dimensions. Okay? 3 dimensions are very important. Is that okay? If you go to 4 dimensions, you can actually remove them, right? You can remove these crossings if you have one extra dimension. For example, if you are saying that I am going to be on a 2-dimensional board only, then this curve and this curve, if I say that I am the ant on the board, this curve and this curve are distinct. But if I say I am in 3 dimensions, I can use the 3rd dimension to pull it out and make it equivalent. Okay? So these are different in 2 dimensions, but you can make them equivalent in 3 dimensions. Okay? These two are equivalent. So this is what you can call it as a Reed-Master move 1. The Reed-Master move 1 is where anywhere in any region, okay, so I can have some non-trivial entanglement happening here and I can have a additional thing, some region you pull it out. If this is equivalent to, so I'm going to confine myself to 3 dimensions, not to 2 dimensions. And whatever I am going to draw on 2 dimension will be a projection with overcrossing and undercrossing to take care that I am in 3 dimension. And here, if I add an additional twist, right, I can always remove this additional twist. Okay, this twist can be done either as overcrossing or undercrossing. Both can be done. But you can see that this is equivalent to this in 3 dimensions. Okay. So whenever we want to say, give a, you know that in 2 dimensions, suppose I give you if I give you some kind of an orange, surface of an orange, or if I give you a donut in 2 dimension, so let me call this as, technical term in mathematics, we call it as 2 sphere. It's a 2-dimensional surface. Our globe is a 2-dimensional sphere, and this one is like a donut or a torus, which is technically called as T2. Suppose I want to say that these two are different. You know it is different. There's a hole inside, which we call it as genus. But you need to give a quantity, a mathematical quantity, which will tell me that a mathematical quantity for S2 and a mathematical quantity for T2 are very different. And you know what that mathematical quantity is? It is what we call it as an Euler characteristic. Right? Euler characteristic which is denoted by chi is denoted as 2 minus 2g. Right? And that quantity distinguishes all the 2D surfaces. You can have many more 2D surfaces that you can take a circle with many more genus, You can have objects like this. And this S2, you can also show that any polygon you can kind of push or pull. As long as you don't cut and paste, you can make them topologically equal. Okay, so the topology of S2 is different from T2, and these are sometimes called as a genus CG, a Riemann surface, denoted as sigma G. Okay, so these 2D surfaces can be distinguished by the simple quantity. Similarly, I want to find a quantity here which can distinguish. These two should be same, right? If I draw this diagram and ask you to count the quantity, someone gives you this diagram, we know that these two are equivalent. We want that quantity to be same, okay? So let me say that V of some quantity, I don't know what this is. I want this to be equal to V of this. Then you can say that it is a not invariant. Okay. So this is not the only Reidmaster move. This is not the only move. You have many more moves. That has been systematized in the mathematics literature. This is one move. You have Reidmaster move 2, where you can, in any particular region, you could have others are all untouched. If you have in any region, if something where you can see that this is same as okay. So you can do this where it may look as if there are, if for example in this unknot, if I taken this as half link, instead of this, if both were, undercrossing, this is not half link, right? This is same as unlink. So you have to see that if you can do the read master move 2, you can actually get the same invariant. So if you write the invariant for this, it should be same as the invariant for this quantity. Giving you an example, but instead of here you could put some non-trivial entangled region, you could put a non-trivial entangled region, right? And then you will see that the non-trivial entangled region and non-trivial entangled regions are here. And the invariant should respect this move, and this is called read master move 2. Okay. R2. And the last one, the last move, which is called the read master move 3, you can have a so if suppose in some region of your knot we focus on this, you can slide this below. Okay, so you can slide this below. So this is read master move 3. Okay. A couple of important things which I want you to know in read master move 1, which I have taken it in this example, you see an additional twist. Okay. In read master move 2, there is no additional twist. If you count here, you have to also try and see what is the right. And to do the right, you have to give some signs. I'll come back to it. And you can show that there is no additional crossings in going from one to the other, including here. Okay. So there are two types of knot invariants. One is called ambient isotopy. Invariants. So this one, the invariant should be such that if you take a knot K, it should be same as K prime, where K prime is related to K by R1, R2 and R3. Okay. So all the three moves are allowed, and whatever quantity you are going to fix, that quantity should be the same if you do the read master move 1, if you do the read master move 2 or read master move 3. Is that clear? There is another class of invariants which are called regular isotopy invariant. Where your V of K, so let me call it by some other symbol, let me call it as P of K, to be equal to P of K prime, where K prime is related to K by only read master move 2 and read master move 3. Okay. So examples of these in the mathematics literature are your Jones polynomial. We'll do the Jones polynomial also, but let me just give you here the example will be a bracket polynomial. Okay. So what I am trying to insist here is that if I work out regular isotopy invariant for this, if I work out the regular isotopy invariant for this, it will not be the same as regular isotopy invariant for this, because these two are related by Reidmaster move 1. Okay? And you may ask, why are we insisting on this regular isotopy invariance? The regular isotopy invariants are sometimes referred to as framed knot invariants. I am confining to knots, but you can do it for general links also. A framed knot invariance. And these framed knots play a crucial role in getting new tree manifolds. Okay, so there is a procedure. So let me explain that procedure. So what are the simple three manifolds? Just like I wrote the two manifolds here. The simple three manifolds will be S2 cross S1. You can have T2 cross S1. Okay. So the way you can say is, you have a sphere, you take a line and identify that line after some point, so you can draw it like a circle at every point. So that is S2 cross S1. T2 cross S1. There is also situations where you can take an R3 and identify all the points at infinity. If you did it for R2, what will you get? You get the S2, right? So the same thing you can do here with identifying all the points at infinity, and that you can call it as S3. This is the 3 sphere. Formally S2 you can give an algebraic equation, right? You can write x2 as embedding in 3 dimension with this condition, right? Where this is the radius of the 3 sphere. If I want to write S3, then you will have there is also other ways in which people can write this, as writing x plus iy as z1 and z plus I omega as z2, and you can write mod z1 squared plus mod z2 squared to be equal to r squared. Okay. So why did I bring this complex coordinate? Now we can start seeing other kinds of 3 manifolds. Let's say S3 mod ZP. These are sometimes denoted as lens space LP, 1. So they will also, the coordinates on this 3 dimension can also be given by the same equation. In addition, you will have an equivalence relation, Z1, Z2. There was no equivalent relation for your S3. Here, can you see the board here below? Yeah. S1, S3, so you will have Z1, Z2 to be related by a root of unity. Okay, where omega is the root of unity, pth root of unity. Okay. So these are called lens spaces. There are also more variants of these lens spaces, and those lens spaces are called LP, Q, and they are given by the same equation, but Z1, Z2 is identified as where P and Q are co-prime. Okay. Okay, I'm just listing a few. Here you could add sigma G cross S1 also. Okay. So I'm just listing you a few three manifolds. The reason is that all the knots are non-trivial in 3 dimensions. And using these knots, you could construct. You can try to take the knots in S3. S3 is closest to R3. No equivalence relation, nothing. It looks locally like a flat 3 dimensions. Of course, you have to remember at infinity you have to identify all the points. So here you can do all the computations of knot invariants. We will go through those details. Once we have that, there is a procedure which is called surgery. I'm not a doctor, but the procedure is called surgery, where you take a knot inside S3, and then we'll go through that. You can do a tubular neighborhood of. So you basically take, let's take this to be denoting S3. Okay. Let's take the simplest knot, which is the unknot, which I started with. And then you thicken the knot. Basically, you take a tubular neighborhood, means just thicken it into forming a kind of a tube around this knot. Okay. Pull it out. Pull it out of this 3 manifold. How will it look? You will have an object with the hole here. Okay, so let me try and keep it like a hole here. You will have one more, which is that thickened piece, right? You've taken the thickened knot, which is also, the knot will be here, okay? You have thickened it and taken a tubular. Both of them have the torus boundary, okay? So this is like a cycle tube with the air included, which means it's 3 dimensions, and the boundary is going to be a 2-dimensional torus. Okay? On the 2-dimensional torus, you have 2 non-trivial cycles, right? By cycles, what I mean is that if suppose I am only on the surface of this 2 torus, I can have a cycle which is called as a meridian, and along this knot which I had, I can also take one more cycle on the surface of the 2 torus. That is what we will call it as a longitude. Okay? And there will be a similar thing here. Right? So now I want to do some kind of a mapping between the meridian and longitude to the meridian and longitude here. Suppose I do a mapping where I try and take a map. Let's say a map where I try to relate the meridian of, let me call this as a unknot complement. Sometimes this is denoted by S3 by a knot. These are notations which you will see in many books. So now take the unknot complement. It also has the torus boundary, oppositely oriented torus boundary to this. If you just fit it back with this map, which is an identity map, you will get back S3, right? S3 with this unknot. If I don't put it as an identity map, suppose I take the meridian to longitude, longitude to meridian. Okay, so such maps you can do. If you do that, what you will end up getting when you glue back after putting this map, suppose this takes from meridian to longitude, okay, vice versa, if I do that. What I will get after you use this map and I glue it back, I will end up getting a new 3-manifold. Let me not tell you what that new 3-manifold is. Okay. It's not very easy for me to visualize, but in some cases you can actually visualize them and show that it be a new 3-manifold. And I will list for you, this is what is the licorice-Wallace theorem. So licorice-Wallace theorem says surgery of knots, I'm going to take it to be frame knots, okay, frame knots in the sense that only reed master move 2 and 3. If you had replaced this unknot by putting an unknot with an extra crossing, the licorice-Wallace theorem says surgery by taking a cubular neighborhood and doing a map, okay, the same map let's take, you will get a different 3-manifold. Unlike your ambient isotopy invariants, ambient isotopy will not distinguish this and this, but the surgery is going to be on frame knots, which is going to distinguish whether you do a surgery on an unknot or the surgery with some extra twist. Sometimes we call it as a framing 1. Okay, so this is denoted as unknot with +1 if it is, over crossing. If you make it under crossing, you can call that to be -1. So if you do it on this, you will get a different 3-manifold. Okay, so let me list what I am trying to say before I get to okay, so licorice-Wallace theorem So I am writing, not technically, there are many things, small things I have not really mentioned here. It should be oriented and so on. So I'll come back to it. But at least pictorially you should get a feel that when you do a surgery on this, and if you do a surgery on an unknot, or if you do a surgery on an unknot with a self twist, which I call it as unknot with framing +1 or -1, you will end up getting a different 3-manifold. But if I write the not invariant and I claim it to be ambient isotopy invariant, the way Jones polynomial is written, this is not for surgery. The not polynomials, if you want to compare with the mathematician's work, we work with this case, which means the ambient isotopy invariant for an unknot or unknot with additional twist will be the same. Is this clear? Okay, yeah.
Yeah, so the way I'm used to surgery being defined, right, is that I have some number with it. And here it seems like, well, you say specifically that meridian goes to longitude, right?
Yeah. So this is one special
longitude?
case. Huh?
Which longitude?
Yeah, so I said this is the map between the link complement T2, okay? Sorry, T3 I should say, right? The unknot, the tubular neighborhood of This is the knot which I took, the tubular neighborhood of it. This has longitude and meridian. This also has a longitude and meridian because
Yeah,
this.
but, how do you define longitude?
Where? On the boundary.
But how do you define longitude? Because I mean, you could define it as a curve, right? That
Yeah.
kind of is a generator of the homology of that thing.
Yes.
But there are several.
So if you make it as a solid torus, one
Yeah.
of them will be contractible cycle. That is the meridian.
Yeah.
Other one, longitude, is non-contractible.
Yes, but there are several of those.
Uh,
So if you take a longitude and you add a meridian.
yeah. So those equivalence relations you have to keep track of it. Yeah, I agree.
Yes. So which longitudes are you?
Okay, I'm just taking a simplest one, the conventional one, which looks like the convenient
What if I
one.
have a trefoil?
Yeah. So let me explain that also. If you had a trefoil, okay. So what I will do is, I will take F. So always I'm going to do a transformation, which is going to take me. So let's draw the trefoil. Okay. So let's take that this is S3 mod trefoil, and I have this with this knot which you're going to have would have gone 3 times along the meridian, right? And then it would have completed. Because trefoil can be seen as a torus knot,
Yeah.
where you can wrap it on the meridian twice
Yeah.
and close it along the longitude.
But it goes twice, right?
Huh?
Doesn't it go twice around the longitude?
Yeah, so you complete it by closing it, right? When you go through this, you have to get back here, right? You take the thread.
But it goes twice. No?
Yes. 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 Yeah. So you take that, and I'm going to. This still has a toral boundary, right?
Yeah.
It has a meridian and a longitude. Once I've drawn this on the boundary, I have a meridian and a longitude because it's a torus knot which is drawn on the torus with a fixed meridian and a boundary. Yeah, what is the confusion? Maybe I'm missing something.
That like it's not exactly unique. What a longitude is. So
Because you're trying to see it as an SL2Z transformation. I understand what you're saying. On the boundary, when you have a torus,
yeah.
if you had something like this is equivalent to taking something like this. That's what you're trying to say, right? The tau and 1.
Yes.
Yeah. So this is what these two are equivalent.
Yeah.
That's what you're trying to say.
Sort of. I think so.
Yes. Yeah. So I am trying to not do that. I'm trying to take a tubular neighborhood. Once I take the tubular neighborhood, I'm not worried too much. I'm trying to take that there is a specific meridian and a specific
But
longitude.
you kind of need to be aware.
At some point, yes, but then I'm trying to do a way of seeing how the mathematician's theorem can be implemented in an algebraic expression. This is what I'm trying to do. Okay? And there when I try to do the F transformation, for me it is like the tau going to minus 1 over tau, according to me. This is the transformation I'm doing. For you, you would say that this is like, it's the same, it's the same class in which it belongs to. Is that what is confusing you?
I mean, so if I draw a trefoil, like the knot diagram of a trefoil.
Yeah. So I'm just trying to tell you that I'm not.
Several curves.
Huh?
I can make several different push-offs of it.
Yeah, but topologically they are all, I'm looking at a topological invariant also, right? You're doing a lot of push-ups. It's not what I'm interested in. I'm interested in taking a trefoil, thicken the tubular neighborhood and take it out, and I'm trying to say that there should be a map with a non-trivial map. So this is a very simple map I gave you. But every two boundary you will have on a torus, you will have a meridian and a longitude. Right?
The longitude needs to be specified about.
Yeah. Okay. So I'm not really specifying it, but if I take this and I put a map I know how to relate my knots in S3 to a 3-manifold. This is all I'm claiming.
Okay.
And these results have been validated with the 3-manifolding. Okay. So, yeah. Okay. Besides that argument, what I'm trying to say is I am interested in taking knots in S3. Okay. And I would like to write summation over. So the knots will have some kind of an identity which I want to put it as some kind of a transformation. And from here I should get some new 3-manifold. Okay. This is all I'm doing. Fine. We can talk maybe after. So this is what is my algebraic way of relating different 3-manifolds, invariants for different 3-manifolds using the knot invariants in the theory, and the knot invariants have to be frame knot invariants, which means it has to only respect Reidmaster move 2 and 3. Is this clear? At least algebraically I would like to validate what the theorem says, and I'm not really too much getting on to these equivalents. We'll come back to it. Of course, there is some...
I definitely agree that it only depends on this, that it changes if you do a Reidmaster 1.
Yeah.
The question is just like, I don't know what that manifold is supposed to be.
Yeah, so that is something which I also have been, I wonder how they can visualize various things. But for me, if they are able to visualize, I would like to give an algebraic expression. Just like the Euler characteristic which can distinguish a torus from S2, I can give an algebraic expression which can distinguish, let's say, S2 cross S1 from S3, or the length space LP, 1 from S3. Okay? Fine. Okay, so this is why I'm saying that knowing knot invariants is very important, because these knot invariants play a role through this Licorice-Wallace theorem to help me to write invariants for 3-manifolds. Okay. Since she asked this question, I also want to say that just like Reidmaster moves, this is not unique. Okay. There can be a knot K and a K prime which are related by Kirby moves. Okay, 1 or 2. Okay. So if you take a knot K and add an unknot with an additional twist, if you do a surgery on this unlinked piece, it is going to give me the same 3-manifold as if you did it with K. Okay. So, or in other words, this with some transformation which I am going to put in here, it should be exactly same as, sorry, I should use the framed invariants, not the, this should be the framed invariants, okay, and not the, so this should be same as the same thing which I do here. Okay. This is a claim that Kirby move 1 and 2, so this is Kirby move 2, this is Kirby move 2, so let me write the Kirby move 2 and the Kirby move 1. So Kirby move 2 is, as I said, some knot K, and you add an additional twist is equivalent to the knot K. Kirby move 1, if you had some additional twists here, okay, this will be same as drawing a half link with the opposite twist is my memory. Okay. Yeah. This should be the opposite twist. So the same knot K you should have with an additional thing which is entangled. So this will become, knot will become a 2-component link, and if you have a twist you can undo it by this. If you did not have this, you will have to add an additional twist. So this two, whether you do this one, the summation over f times, so this f I'm formally writing as a homeomorphism on the boundary, but let's not worry about what this is. If you take p of this k, okay, so let me call this as some, not, this whole thing with this twist is what I'm calling it as k, and then this one let me call it as some h tilde, so p of k tilde, this should be same as, okay. So these are very important. So this f will also change to something else, but let me not worry too much, okay. But you need to write an expression that the summation will depend on the number of components. So there will be so many summations. So there will be two summations here. Similarly here there will be two summations and this side will be one summation. So you need to find what is this quantity which respects Kirby move 1 and Kirby move 2. Then you can claim this object as a three-manifold. It has to respect both, okay? Then it is a good three-manifold. Okay. So this is what is important, that you need to find in terms of frame not invariance or frame link invariance, an algebraic expression. What is this algebraic expression is dictated by that the invariant should not change under Kirby move 1 or Kirby move 2. If it happens, then it's a good three-manifold. Okay. So this is what is, incidentally, there is no well-known classifications of three-manifold. Okay. Two-manifold, S2, T2, as I said, Euler characteristic completely classifies two manifolds. But if you take S3, S2 cross S1, and I don't know what this M is, but I can generate from various knots. Okay. So huge three manifolds. It's not clear. It's not clear whether Z of M I find, and I find Z of M prime. This is done from surgery of a knot or a link. This is done by surgery of another knot or a link which is not related by Kirby move 1 or 2. Okay? If they turn out to be same, it's just an algebraic accident. Exactly like you are not polynomials, which I wrote the ambient isotopy invariant, there could be a knot K and there could be a knot K prime. Let me call it a some other knot where K tilde and K are not related by Reidmaster move 1, 2 or 3. But the polynomial is same, then it is again an algebraic accident. This also tells you then it is not a good invariant. If it is a good invariant, what is the requirement? If K and K tilde are not related by Reidmaster move 1, 2 and 3, strictly this should be not equal to. Most of the cases it is not equal to. Sometimes some of them are equal. Okay? That means what? Such an invariant does not completely classify the tower of knots, tower of unequal and knots. If I want to classify, I need an invariant which is going to be different for different knots which are not related by Reidmaster move 1 and 2 and 3. Ambient isotopy. That has not happened so far. At least the Jones, Homefly, Kaufman, they do find there are knots K and K tilde. There are cases where K and K tilde are going to be same. Okay, so this is why it is an open question. If these two are not going to be, similarly in the ambient isotopy and regular isotopy also. So if you have those knots which are not related by Kirby moves, if K and K tilde are not related by Kirby move 1, 2 and 3, I will get the same 3-manifold invariant, which means 3 manifolds are also not completely classified. Is this clear? Right? So this is a problem which we all want to somehow solve. And that is where we are using the power of Chern-Simons field theory. And we would like to see whether we could solve first order question to first write the ambient isotopy. Of course, from ambient isotopy, I can write the regular isotopy invariant with some framing correction. Once I know these two, then the next one is to go and look for 3-manifold invariant. Yeah.
In K1,
Yeah.
is that supposed to be a hop flinking? Because if I take the right picture, I could do a randomized 2 move
Yeah.
to separate them, and then use K2 to delete that thing.
This one?
So K1 below,
This one?
yeah,
Yeah.
on the right, is that supposed to be a hop flinking?
Yeah. So if I take a hop linking with this and
Okay.
if I remove this out,
Because you have drawn.
I have
two
to undo
overflows.
this with the opposite things. This is what is the Kidman.
The diagram is not correct.
What?
It's 2 over.
Should be linked.
Yeah. Sorry. Thank you. Yeah. Is that what you pointed out?
Yeah.
Okay, sorry. I didn't even realize it should be entangled. Okay? Yeah. So I think this is let me just say what I have said now, and then we can continue in the afternoon lecture after. So I have tried to give you So I've tried to give you a flavor of a knot and then a link, and then I've also said about ambient isotopy invariance for a knot. Also said a regular isotopy invariant for a knot. Whatever I'm saying can be also included for the link. Okay. So this one will respect read master move 1, 2 and 3. So if not K and K prime are related by read master move 1, 2 and 3, the constructed invariant will be equal. Converse is not true. Okay? Converse in the sense, if you had a not K and K prime which are not related by read master move 1, 2 and 3, that could be accidental symmetries. Okay. And here it should be respecting only read master move 2 and 3. And they play a role in the construction of these 3 manifold invariants are written in terms of writing sometimes not invariants, but you should know that some can be not, some can be links. Okay. And the question is V of k equal to V of k tilde not related by. Okay, and similarly Z of m obtained from k and m tilde from k tilde, where k and k tilde are not related by Kirby move 1 or 2. Okay, and or. Okay, so this is all I'm trying to say, that the problem of classification of knots is still a question mark. Hence, classification of three manifolds is also a question mark. Okay, so let me stop here. Is that fine? It's a good thing.
Yeah.
And then we will continue with the constructions of invariants in the next lecture. Yeah.
Thank you. Do you have some more questions before the lunch break? Okay, so we'll continue.